Let's get started with, there we go. Let's get started with Chapter 3. Chapter 3 is applications of derivatives. A large portion of this chapter is devoted towards curve sketching. The idea of how can I look at a function and get an idea what the graph is going to look like. Some ways with our technology, this is not as an important skill because we can just type it into decimals or type it into our calculator and draw the graph. But it still is important because one thing, when we get the graph, do we have a complete graph? Have we seen everything that's important to us? We can tell this by analyzing it. The other thing is, can we find some of those things of interest with this function without having to graph it? So we're going to be spending some time doing that. This chapter has a lot of sections, but first part, a lot of these are kind of short sections that aren't quite as involved as, say, implicit differentiation in last chapter. The chapter is going to finish off with optimization problems. How can we find the best way to do a situation, and then lead us into something called differentials, which is a kind of a segue into chapter 4, which is integral calculus. So let's start with section 3.1, which is extrema on an interval. So understanding the definition of an extrema of a function on an interval, the definition of relative extrema of a function on an open interval, and extrema on a closed interval. This is pretty much a vocabulary, a definition lesson. We'll end up with actually applying these definitions and doing a little work with it, but a lot of this is just getting down vocabulary. So I want to go here. When we're working with this, we're going to be always defining our function on some interval containing a point C. And again, to define what is an extrema, is we're looking for the minimum or the maximum. And a minimum on an interval means that f of at that point C is smaller than f of x for all of the x in your interval, and a maximum when it is greater than f of x for all of your values on that interval. So we call these minimum and maximum values extreme values, or extrema. So again, sometimes going back to quadratics and gravity problems, sometimes you shoot your arrow up into the air, you want to know how high it gets. That's an extreme value. Those are the things we're looking for. Now we talk about absolute minimum and absolute maximum. These are also called the global minimum or the global maximum. So we're saying there's no point bigger than those. So that's one of the things we're looking for. Sometimes our extrema occur at just the endpoint. It's not kind of like the parabola where it's the highest point that goes down again. Maybe the highest point is going to be at one endpoint. You think about an exponential function, your extrema is always going to be at your endpoints of your interval. So that's what we mean by an endpoint extrema. So it's a little visualization here. If we have this function, you notice we're a closed function, a closed interval. Whoops, let's go back. So this has a definite minimum. At this point is the smallest value of the function. This is the largest value of the function. So we have both a minimum and a maximum. If we make our endpoints open, this is an open interval, we still have this is a minimum. It's the smallest value. But we don't have a maximum because we don't actually have an endpoint here. It can always get bigger and bigger and bigger. Now it's going to approach the value of this value you would get if you fold in here, but you never reach this. So this, on this open interval, we do not have a maximum. And now here's just a weird one just to prove a point. We have a maximum because it's a closed interval. That's the highest value it gets. But the minimum here is a hole because we did a removed point here. this would not be a minimum because, again, we do not have this point at that actual lowest spot. So we do not always have a maximum or a minimum on an interval. Oh, there went my mouse. Who cares? So when can we know we can have these? And this is where we get to the extreme value theorem. This is one of the ones we're going to use a lot. If f is continuous on a closed interval, then f has both a maximum and a minimum on that interval. It has to be closed and continuous. If we go back to over here, we're closed, we're continuous, we had a minimum and a maximum. Here we're not closed, so we don't have both. Here we're not continuous, so we don't have both. Now, it can be an open interval and still have a maximum and a minimum, both of them. It can be not continuous and still have a maximum and a minimum. But to guarantee we have both a maximum and a minimum, we have to be continuous on a closed interval. That's the extreme value theorem, or EVT, if we want to use a nice three-letter acronym. So what about other extrema? Just because it's not the absolute maximum or the absolute minimum, we still talk about extrema, and these are our relative extrema. And this is, for example, the point 0, 0. If we look on the interval between -1 and 1, it is an extrema. It is the largest value on that interval. But if we go at the interval from -2 over to 4, you can see here we get up higher, so it's no longer a maximum value. So it depends on what interval we're talking about. So we can refer this as a relative maximum, because if you look in close, it is a maximum value. If you extend out your interval, it might not be. But so when we're looking at relative extremas, we're looking for, hey, is it an extreme value on some interval? Not necessarily the interval of the function we're interested in. So same thing with the relative minimum. This would be a relative minimum because if we look on here, it is the minimum, but if we extend out farther, here we're going to get lower. So now again, nice formal definition. For a relative extrema, just means there is some open interval containing C on which C is a maximum. Or there is an open interval containing C in which C is the minimum. It does not have to be the defined interval of the function, but it's just saying, is there any open interval I can set up on which that point is a extrema? Then it is a relative extrema. So, where do differentials tie into it? This is where what's going to get to us. This theorem here, relative extrema occur only at critical numbers. That sounds important. Yeah, if it's a relative minimum or relative maximum at x equals c, c is a critical number. What's a critical number? A critical number is defined by either a value of x, this value c, where f prime of c equals 0, that's a critical number. Let's go back. Or if f is not differentiable at c. If the derivative does not exist at c, kind of things like we looked at the absolute value, has that point where we have that peak, you can't find the derivative at c. That is a critical value, a critical number. So you could get a relative extrema at those points. So it comes down to find relative extrema on a closed interval. One of the first things we're going to do is find the critical numbers. So in order to find the critical numbers, we're going to take the derivative, find where the derivative doesn't exist, find where the derivative equals 0. We're going to evaluate f at each critical number. Then we're going to also evaluate at the endpoints, because again, the endpoints could be a maximum or a minimum. And then we look at all of these. The least of these is the minimum, the greatest is the maximum. And as long as, again, going to extreme value theorem, as long as this is continuous on a closed interval, and that's what we have, continuous on a closed interval, there is guaranteed to be an absolute maximum and an absolute minimum. But this is also going to help us find the relative ones. If we need those, we can find that. So, but right now we're just looking for the absolutes when it says find the extrema. So, let's do some of these. Bring this up so I can write on it. We're going to do this first one. I'll work this with you. No, let's plop this up so you can actually read what the problem says. I'll work this through with you, and then we'll do a couple more examples where I'll let you give it a try. If you want to think, hey, I got it now, I'm going to do it on my own, go for it. Pause the video, find your answers, and then we'll come back to the video and see if you agree. So our first thing we're going to do is find the critical values. And to do that, we need to find f prime, to find the derivative. So the derivative of this is a nice polynomial, so we can just use our general power rule, 4 times 3x to the third minus 3 times 4x squared. So f prime of x is going to be 12x cubed minus 12x squared. This is a nice polynomial, so the derivative exists. This is going to exist on all values on the interval -1 to 2, so I don't have to worry about places where the derivative does not exist. So now I'm going to set this equal to 0 and say 12x cubed minus 12x squared, which very nicely has a 12x squared I can factor out. And I'm going to get x minus 1. So this is going to say x can equal 0 or x can equal 1. So I have critical values at x equals 0, x equals 1. So I want to evaluate the function at f of 0 and at f of 1. I also need to look at the endpoints. So I have endpoints at x equals -1. I have to find f of -1. I have x equals 2, so I have to evaluate x equals 2. And then I just basically plug these into my original equation. 3 times 0 squared minus 4 times 0 to the third power is going to equal 0. That's pretty easy. If I plug in 1, I get -1. If I plug in -1, I get 7. And if I plug in 2, I get 16. So this is my biggest. So I have a maximum at the point 216. Actually, let me rewrite this. Looking at my extrema, circle this again. My maximum equals 16 at the point 216, or when x equals 2. My minimum is going to be -1, and this is going to be at the point 1, -1. So these would be my extrema my absolute maximum and absolute minimum on that interval. Now here, this one, 0, should be a relative. I don't know from looking at this, though, whether that's a relative maximum or a relative minimum. The endpoints I'm not going to define as relatives because I can't make an open interval around an endpoint. So this is probably a relative, and we will learn with as we go into further sections, what kind that's going to be. So let me clear this off. Oops. And give you this problem to try. So again, my first step is I need to find my critical values. So I need to look at the first derivative. 2 minus 3 times 2/3 times x to the negative 1/3 is going to be here, this is nice, 2 minus 2x to the negative 1/3. Or I'm going to rewrite this, factor out my 2, 1 minus 1 over the cubed root of x. Now when I look at this, I have x in the denominator right now, so I know the derivative does not exist when x equals 0. So that means this is one of my critical values where x equals 0. Notice x equals 0 does not mess up the function. I can plug 0 in here, but I can't find the derivative at that point. Then I look and see, where does 0 equal 2 times 1 minus 1 over the cubed root of x? And that's going to be where 1 over the cubed root of x equals 1. So x is going to have to equal 1. And again, I also have to look, are these actually on my interval? They're both within my interval, so that's good. So I'm going to check my critical values here are x equals 0 and x equals 1. And then I have my endpoints of x equals negative 1 and x equals 3. So I plug all of these values into my function. F of 0 is 0. F of 1 is negative 1. F of negative 1 is a negative 5. And f of 3 is a negative 0.2403. So now we have those. We just say, what's the biggest? My maximum is 0, and that's at the point 0, 0. My minimum is going to be negative 5, and that's at the point negative 1, negative 5. So again, this one has one of the extrema is an endpoint, the other one is inside the interval. This is very likely a relative extrema, but I can't even guarantee that. Again, we'll look at that some more. So I got one more of these for you to try. And where would be the fun if we didn't do one with trig functions? So go ahead and try your hand at this one. So again, I'm going to start off with, to find my critical values, I'm going to find my derivative. 2 sine of x is just going to give me 2 cosine of x. I like that one. That one's easy. Here we have cosine 2x. If you really wanted to, you could pull out your trig identities and break that down into using the double angle formula for cosine. I never remember that one. I got to look that one up. But I'm just going to use the chain rule. So the derivative of cosine is a negative sine. And then we have to take this times the derivative of 2x, which would be 2. So f prime of x is going to be 2. I got a common 2. Let's take this out. The cosine of x plus the sine of 2x. Derivative's pretty easy to find. Now comes the real fun. To find our critical values, well, cosine is continuous, sine is continuous, so both of these are fine. We don't have any problems with places the derivative does not exist. So we come along 0 equals 2 times the cosine of x plus the sine of 2x. At this point, you're going to need to get out your identities. And remember that the sine of 2x is 2. What do I have equals there? Okay. 2 sine x cosine x. So we have 2. We got a common cosine. So 2 cosine x times 1 plus 2 sine x, which is, I don't know, I think that's much easier. Well, definitely here, I don't want to mess with that. So 2 cosine of x, this is where cosine of x equals 0. So x is going to be pi over 2 and 3 pi over 2. Remember, when we are doing calculus with trig functions, we have to always be using radians. All of this, our rules, our guidelines, our basic formulas are based on the idea of radians. So we got to stick with that. This one we get 1 plus 2 sine x equals 0. So the sine of x has to equal a negative 1/2. So x is going to be 7 pi over 6 and 11 pi over 6. So remembering your trig facts or remembering your unit circle or using that trig cheat sheet might be very much of a help when you're trying to do some of this stuff with trig. But so here we have 4 critical values. So we're going to have to evaluate at pi over 2, 3 pi over 2, 7 pi over 6, 11 pi over 6, and then look at your endpoints, which are going to be at 0 and 2 pi. When you're doing this on your calculator, I would definitely take advantage of, we talked about in class, setting up your table so that instead of being auto, it's on ask, so you can type this formula into your calculator and just say, give me these values. You can plug it in. You can do it however you want. But plugging these in, this is going to give me 3. This was negative 1. This was negative 1.5. This is negative 1.5. This was negative 1. And this one was negative 1. So, my extreme values. Let's clean that up because that's confusing. Because I did that. Make that look like a 1. Okay. My maximum here is at 3. So I have a max of 3 at pi over 2. You notice this one has 2 minimums. It's hitting this lowest value at, whoops, and they're not those, right? Okay. 2 minimums, and it's hitting it at 2 places, which is not surprising because both sine and cosine are periodic and they repeat like crazy, right? So we're going to have your minimums are going to be a negative 1.5, and this is going to be at both 7 pi over 6 and 11 pi over 6. So that's extrema on an interval. Here's your assignment. Go ahead and start working on those. Bring your questions to our help session. Enjoy.